Video presented to you by Unique to Billions e-learning. Please subscribe it and press the bell icon. In the first section of this video, we are going to see whether photoelectric effect can explain with the wave theory of light. According to the wave theory of light, light is an electromagnetic wave consisting of electric and magnetic fields with a continuous distribution of energy over the space over which the wave is extended. This theory also says that more intensity means more energy. Now we are going to see how wave theory explains photoelectric effect. According to the wave theory, when a light falls on a metal surface, the energy is distributed over the metal surface. We know at the metal surface there are number of free electrons. The free electrons at the metal surface where the beam of electrons falls receive energy continuously. When an electron receives energy more than the work function, it will eject out. This resulted in photoelectron. We are going to see here whether wave theory explains our observation in the experimental study correctly. According to wave theory, a beam of light of any frequency can emit an electron from the metal surface if it applied for a sufficient time. What was our observation? Our observation is that we required a minimum frequency nu 0. We call it is a threshold frequency which required to emit an electron from a metal surface. So this explanation contradicts the observation. This also expects that when light falls on a metal surface, it may take time for electrons to absorb enough energy to eject out. That is, there may be a time lag between incident light and the emission of electrons. But our observation is that photoelectric emission is an instantaneous process. There is no time lag between the incident light and the emission of photoelectrons. This also contradicts our observation. According to wave theory, more intensity means more energy. So, if the intensity of radiation increases, electrons will absorb more energy and thus have more kinetic energy. That is, the maximum kinetic energy of emitted electrons is expected to increase with increase in intensity. But our observation is that maximum kinetic energy is independent of intensity of incident radiation. That means this is also contradicts our observation. That is, wave theory of light is unable to explain the basic features of photoelectric effect. Now we are going to see Einstein's photoelectric equation, energy quantum of radiation. In our earlier sections, we saw that photoelectric effect is that phenomenon in which if a light with a frequency more than threshold frequency incident on a metal surface, electrons are emitted. We also saw that a minimum energy equal to work function phi must be given to electrons to bring it out of the metal surface. This phenomenon of photoelectric effect was explained by Einstein in 1905. In this theory, he considered radiation energy as a group of discrete units or packets of energy called quanta of energy of radiation. Each quantum have energy h nu, where h is Planck's constant and nu is the frequency of light. Let us consider a metal surface with free electrons on the surface of that metal. In photoelectric effect, we studied that when light falls on a metal surface, the electrons will be ejected out if it gains an energy more than the work function. According to this theory, the photoelectric effect occurs when an electron absorbs a quantum of energy h nu of radiation which is greater than the work function, then the electrons will be emitted out with a maximum kinetic energy which is equal to h nu minus work function. We know the relation between frequency and the wavelength, that is, the frequency nu is equal to c by lambda, where c is the velocity and lambda is the wavelength. So, this expression can also be written as h c by lambda minus phi. This equation is called Einstein's photoelectric equation. This is the maximum kinetic energy of an emitted electron. The electrons more tightly bound will come out with a kinetic energy less than the maximum kinetic energy. They may lose energy to the metal in course of collision with the atoms of the metal. Thus, if it makes collisions before coming out, the kinetic energy will be less than the maximum kinetic energy. The actual kinetic energy will depend on the total energy lost. Thus, the kinetic energy of electron coming out may be anything between 0 and the maximum kinetic energy. Note that the intensity of light of a given frequency is determined by the number of photons incident per unit area per unit time. Now we are going to see whether this theory can explain our observation of photoelectric effect. Look at this equation. This equation clearly says that K maximum, that is the maximum kinetic energy, varies linearly with frequency nu. We know our observation was also the same. Also, intensity here is the number of photons incident per unit area per unit time. According to this theory, the photoelectric effect arises from the absorption of a single quantum of radiation by a single electron. That is, it is independent of the number of photons incident per unit area per unit time. Thus, the maximum kinetic energy is independent of the intensity. What was our observation? Our observation was also the same. That is, the maximum kinetic energy is independent of the intensity. Now we look into the other case. The maximum kinetic energy is a non-negative value, which implies that photoelectric emission is possible only if h nu is greater than phi, the work function. Let work function is written as h nu 0, where nu 0 is a frequency which is equal to phi divided by h. This gives an idea such that h nu must be greater than h nu 0. In other words, we can write here that the frequency of incident radiation must be greater than a frequency nu 0. We call it as the threshold frequency. This theory says that there exists a threshold frequency below which there is no photoelectric emission. Our observation is also the same. That is, there is a threshold frequency for the metal surface below which no photoelectric emission is possible. One of our observations is that if nu is greater than nu 0, then the photocurrent and intensity of incident radiation are directly proportional. Let us look into our figure for understanding this. According to this theory, the intensity of light is the number of photons incident per unit area per unit time. So, if intensity is more, that means that the number of photons incident per unit area per unit time is more. So, as intensity increases, more energy quanta available. Therefore, a greater number of electrons absorb the energy quanta and will eject out of the metal surface. Therefore, it clearly explains if nu is greater than nu 0, then photocurrent is directly proportional to the intensity of incident radiation. So, this observation is also explained with this theory. And now we are going to see another observation. We observed that this phenomenon is an instantaneous process. Here, the absorption of quantum of energy by an electron is also an instantaneous process. That is, the photoelectric effect arises from the absorption of a single quantum of radiation by a single electron, and it is independent of the intensity. So, the process is instantaneous and intensity only determines how many electrons are emitted, that is the photoelectric current. Thus, we can say that this theory explains the observations of photoelectric effect. We also know that the maximum kinetic energy of an emitted electron is given by the equation K maximum is equal to EV0, where V0 is the stopping potential. Combining this with Einstein's photoelectric equation, we can write it as EV0 is equal to h nu minus phi. We can rewrite this for the equation for stopping potential. V0 is equal to h by E into nu minus phi by E. This equation gives an idea about the relation between stopping potential versus the frequency. This equation is an equation of a straight line with a slope h by E and is independent of the nature of the material. Later, Millikan proved this by determining the value of Planck's constant h through experiments and is observed to be very close to the value determined in an entirely different context. Now we are going to see the particle nature of light, that is the photon. We have seen in previous section that light is behaved as if it was made of quanta or packets of energy with energy equal to h nu. It is also found that the light quantum can also be associated with a momentum P is equal to h nu by c. This can easily derive. We know energy of a quanta is equal to h nu. We also know the Einstein's energy mass relation E is equal to mc square. Therefore, we can write h nu is equal to mc square, or we can write mc is equal to h nu by c, where mc is the mass into velocity, which is the momentum. Therefore, momentum p is equal to h nu by c. A definite value of energy as well as momentum is a strong sign that the light quantum can be associated with a particle. This particle was later named as photon. So we are summarizing photon picture of electromagnetic radiation as follows. 1. In interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. 2. Each photon has energy E is equal to h nu and momentum P is equal to h nu by c and speed c, the speed of light. 3. All photons of light of a particular frequency nu or wavelength lambda have the same energy E is equal to h nu, that is equal to hc by lambda, and momentum P is equal to h nu by c, that is equal to h by lambda, whatever the intensity of radiation may be. By increasing the intensity of light of given wavelength, there is only an increase in the number of photons per second crossing a given area, with each photon having the same energy. Thus, photon energy is independent of the intensity of radiation. 4. Photons are electrically neutral and are not deflected by electric and magnetic fields. And last, 5. In a photon particle collision such as photon electron collision, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision. The photons may be absorbed or a new photon may be created. Thank you for watching this video. Keep learning. If you are not yet subscribed to our channel, please subscribe it. Also, please like and share this video.